So let's go to the slides. I'll paste the link like usual. Chat, cool. All right, so that's the general, that has links to everything. And then if I get it right, the link to this week will be, yeah, that should work. Cool. So that's this week. Oh wait, let me make sure people can see my screen. Here, that's what I want. Okay, cool. So yeah, we're just going to talk about k-nearest neighbors for a minute and then final review. So yeah, remember from last time that like this is, you know, people in statistics and machine learning will complain about this definition either way, but in general, statistics is more oriented towards like explanation or understanding why an independent variable has an effect on the dependent variable, or especially like social science. So, okay. Whereas machine learning like it just came out of a different paradigm, which is prediction, right? It came out of like people wanted to predict whether or not an email was spam, right? Or people wanted to be able to predict what digit people were writing on an envelope. Those are like the two biggest things that put machine learning on the map. So yeah, there's a bunch of different tasks. And these tasks exist in either, there's like statistical ways of doing them and machine learning ways, but for classification, what k-nearest neighbors is for? Oh, hand raised. Yeah, what's up, George?
I had a question about the homework this week. So I noticed that if you change like the number of decimal places on the Excel file, that would differ like the answers that you got. So the like, are they gonna take that into consideration?
I what? I don't.
So like the homework, like the FSI scores. So the default setting is only displaying to the 10th place. But I like increased it to like 4 decimal places, and that like shifted my answer by like a little for some of the questions. So I was just wondering like, are they gonna take like rounding into consideration?
It really depends on the question, but yeah, you should not round to the extent possible because rounding, yeah, just gives less precision. So I'd recommend, yeah, not rounding.
And just like, a quick follow-up, sorry about that. Question 1 was a bit like I was a bit confused. Were we supposed to transport the Excel file into a CSV, then upload that? Or were we supposed to just in Python upload it as an Excel file and then transfer it into a CSV?
I can't really answer questions on the homework in these sections, but whatever satisfies the question, I don't know. I'm not, we've been told to just teach the stuff in the section and then answer questions on the homework through email and during office hours. Yeah, Sky? Question? Sky? Hand raised?
Couldn't unmute myself for a while for I don't know reason. Since we're talking about the homework, I wonder, so for
Well, not really. I didn't want to talk about the homework. That was
yeah, just a quick question, because last week's homework, it requires us to delete all the like the empty cells, empty columns and rows from the Excel file. So I did it manually in Jupyter Notebook. So I wonder, is there any shortcuts we can do it in Python? I tried to Google that, and some of the people gave some suggestions, but it's just not working for some reason. Yeah, I tried drop NA, but the like the empty columns and rows are not.
I mean, these are questions that are good for email or office hours. I don't know. Let's look at if the question says anything about whether you need to do it in Python or not.
Oh no, it's not like for grading purposes. It's just out of curiosity. How would you approach?
Oh yeah, so out of curiosity, then yeah, you would want to use well, you wouldn't want to use drop NA. Well, drop NA would delete the rows that only have NA, right? So
yeah. So
for,
what about empty rows that come within the file? So I tried drop NA and it's not working.
for this one, question 1.
Yeah. Well, it might not for question 1, but I remember in later, like, because
Okay, I see.
yeah, run the regression, and then it requires you to not have like tons of empty rows and columns.
I see. Yeah, and George, I guess this answers your question too. That's kind of weird. It says to, I see. I'm sorry. I didn't mean to brush your question off, George, because I didn't realize. I thought that they linked to a CSV version. But yeah, no, if they link to an Excel version, then yeah, just then you can do either one. You can load it as an Excel, because Pandas does have pd.read Excel function, or you can open it in Excel, convert it to a CSV, and then do pd.read CSV. Either of those will work. And then Sky, your question? Well, yeah, it's okay. Well, let's see what this looks like. Let's see. NYU, cool. So, wait, which ones are empty?
There's just a bunch of empty rows and columns.
Yeah, so when you open an Excel file, even though your valid inputs are only like certain rows or column, but it's autofill more rows and column, even though they're empty. And when you import the file, those empty stuff come with within.
Okay. Let's try it. Yeah, this will be good. I'll just like do it here. NYU, and then it was, what was it called?
You should probably download it as a CSV, because if you just do the read Excel thing, I'm pretty sure it just like takes care of the empty rows and columns for you.
Oh, well, let's just try it. Let's see what happens. All right, pd.read Excel. FSI 2020. Oh yeah. I still don't see any empty.
Yeah, you need to like upload it as a CSV.
I convert the Excel into CSV, and then they have like so many empty rows and columns. Maybe.
Oh, well then just don't do that, right? Can you just do this?
Yeah, I could just do that. I didn't know that's the problem, but now I see. Thank you.
if you get points off because you loaded it as an Excel instead of a CSV, just tell me, because I mean, yeah, that just seems annoying. I mean, it's like we can't really require you to have Excel. Like Excel's like a paid, like an expensive program. So, I mean, you get it for free through NYU technically, but yeah, I mean, Pandas has a read Excel function, so you may as well use it here.
Right, thank you.
Yeah, sorry about that. I know that's confusing. I don't know why they would say read it as a CSV. Like I didn't have Excel until like recently. I mean, like I pirated it. Don't tell. Like I am not paying for Excel. So yeah, don't pay for Excel. That's the lesson here. And it looks like if you load it as XLSX, everything seems okay. Yeah, everything seems good. Cool. Cool. Okay, hopefully that answers the questions. Great. Back to K-nearest neighbors. Oh, should I, Sky, is because your hand is still up, are you good? Or do you have another?
Oh, yeah, I'm good. I forgot to
Okay.
raise my hand. Thank
No,
you.
that's fine. I just wanted to check. Cool. All right. Thanks. Yeah. Sorry, I was like hesitant about it. I've gotten yelled at for not covering enough material in the sections. Okay, so binary classification, yeah, that's like the spam example that I gave, right? Where given like say a count of words in an email, you know, like if it says like free $1 million, you know, $1 million, that might be like indicative of spam. So your like independent variable there would be the words in an email. And then your dependent variable would be you're trying to predict whether it's spam or not spam, right? And so the way that would work is like you'd have a person go through like a set of like 1,000 emails and be like, oh, this one's spam, this one's fine, this one's fine, this one's spam, right? And you'd have a bunch of examples. And then you would split those examples into a training set and a test set. And you would try to learn what features, right? What properties of the independent variable predict spam. And then you'd want to classify it as spam. So that'd be like y outcome variable equals 1 or not spam y is 0. Similar case, multi-class classification. You want to classify a given observation into one of n categories, right? So that's the handwritten digits example, where you have a picture of a handwritten digit and you're trying to classify it into 0, 1, 2, 3, 4, up to 9. And so there's like a million ways you could do this, but the k-nearest neighbors way is you want to find the k most similar observations that we've seen before, right? So in the spam case, you would find like if k was 5, you would want to find the 5 emails that look the most similar to the one under consideration, and then take a majority vote of those ones. Like if a majority of the ones that looked like this email were spam, then you classify this email as spam. Whereas if the majority of the emails that looked like this one were not spam, then you classify it as not spam, right? So as an example, you can have a problem like given a student's GPA, predict whether or not they will graduate. And there's many different ways you could think to do this, right? You could have tried to find like a threshold, like, oh, most people above this level graduated and most people below this level didn't graduate, and that could be your way of predicting. But the k-nearest neighbor approach is not that. The k-nearest neighbor approach is you just get a data set of previous years with students' GPAs and whether or not they graduated, and then you find the k equals 5. You know, if k is 5, then you find the 5 students with the GPA closest to the student you're trying to predict. And yeah, if a majority of them graduated, then predict that this student will graduate. Otherwise, predict that they won't, right? So that's the idea, and we'll do an example. But graphically, it looks like this, right? So you have, let's say like x-axis, just think like x-axis here is GPA, and maybe y-axis here is SAT score or something. And then the stars are the ones who graduated, the triangles are the ones who didn't. But now we have this new person who has this GPA and this SAT score, and we're trying to predict whether they will graduate or not. So what we do is we calculate the distance, right? Like we calculate how far their SAT scores and GPA are from these other examples, and then we take a vote of the 3. So we find that this one, this person, this student, and this student are the 3 closest to them in like GPA score and SAT score. And here K equals 3. And so we take a vote, right? And we find that 2 of the 3 nearest neighbors didn't graduate and only 1 did. So we predict that this question mark student doesn't graduate. Cool. So yeah, evaluating it is it's like really frustrating when you first learn machine learning, how fuzzy the evaluation can be, because you would just think like, oh, let's just compute the number of students that it gets correct and the number of students that it gets incorrect, right? But the problem with that, the reason you generally don't want to do this is because a lot of times so the computer will try to like almost be too smart, in the sense that if you just tell the computer like, oh, just get really high accuracy, what will happen is, so for example, let's say that like 99% of emails are normal emails and only 1% of emails are spam, then it's going to learn like, oh, I can get 99% accuracy if I just always guess that it's not spam, right? Because it will just find that, if you select an email 99% of the time, it won't be spam. So if it just always guesses not spam, it'll be right 99% of the time, right? But that's not actually like machine learning. That's just learning that one class is bigger than the other, right? And so that's why we don't want to do this. But instead, what we want to do is we want to use something called like the F-score, which is kind of, you can think of it as just the average of, it's called a harmonic mean. Like the average that you usually take is called the arithmetic mean, where you add them and then you divide by the total number. The F-score is a harmonic mean, which is essentially where you multiply them and then take you take the root of the number, but you don't have to worry about that. The point is it's a thing that takes into account both true positives, TP, right? So that's the accuracy, that's the true positive rate, but then it also takes into account false negatives, right? And since these are rates, it technically also like implicitly takes into account false positives, right? So the point is just that in the spam case that I talked about, this solves that issue where the computer will just always guess not spam, because it will say like, it will penalize them for all the times that it says not spam, but it's actually spam, right? Like it will penalize those higher than it will reward getting things right, because it takes into account that the computer can just get almost everything right if it just guesses the majority class, right? So I know that's like hard to think about, because when we think of accuracy, we just immediately think of like, how many did it get right? But just hopefully that spam example helps, that like you could just have a spam classifier. Like you could have a spam classifier that always says spam, and then it will catch all the spam, right? It will catch 100% of spam, but it will also catch 100% of the emails that you actually want, right? So just think about it that way. Cool. Now, final review. Cool. This is the moment you've been waiting for. So yeah, I wrote like, I think like 27 questions. So I'm gonna go through them here, and then also I'm holding a final exam review on Tuesday at 3:30 p.m. So actually the same time as this, but on Tuesday.
Wait, isn't our final on Tuesday?
No, it's on Wednesday.
Oh, okay.
Yeah, the 9th. Cool. Yeah, the 9th. So yeah, common misperception. So yeah, there's just a bunch of sections. So we'll start with common misperceptions, because they're the things you can most easily like deprogram your mind to think and get free points. So true or false, the p-value is the probability that the null hypothesis is true. And the answer is false. P-value is the probability that we would obtain a test statistic this extreme if the null hypothesis was true, right? So it's not the probability that the null hypothesis is true. Because of the like p-value cutoff thing in scientific journals and everything, like it's easy to think that it's the probability that the null hypothesis is true, but it's not. You shouldn't think of it that way because it's, yeah, statistically like wrong. This one is like a little more pernicious. So true or false? A 95% confidence interval means we're 95% confident that the true value of the parameter is between these two values. That is absolutely false. We have no guarantee that there's no thing telling us that there's a 95% chance that the true value is in the confidence interval. It's just this weird interval that's kind of like outdated. You know, it's kind of from an era of statistics that in like the 1800s, where yeah, it was like if we reperform the experiment many, many times, on average, we would expect the interval, right? The interval would be different every time we perform the experiment. But because of the way that like normal distributions work, basically, we would expect the computed interval to contain the true value of the parameter about 95% of the time out of many, many, many experiments. But it's not like we can't say anything definitive about a particular confidence interval, right? We just know that like if we keep computing the confidence interval a bunch of times, about 95% of the time it will contain the true value, but it's not very helpful. I wouldn't place too much like import in the confidence interval. Yeah, Sky.
Because the way you said it, it feels like each time if we calculate the confidence interval for like several times, and then we each will get a different value for that.
Yeah, yeah. It's not the best measure. It's just kind of a measure that it has to do with the law of large numbers, and it's like, yeah, it just says like because of the way that randomness works, this interval, like, how did I put it? Like it's like, how do I put it? It's kind of, yeah, because okay, we learned in class how the law of large numbers says that like if you sample something a bunch of times, the average will be a normal distribution. So then the confidence interval just takes that like one step further and says like, okay, if we did this experiment a bunch of times, like if this particular coefficient that we saw was a sample from like a bunch of experiments, then we can imagine a normal distribution centered around our coefficient, and then it just says like 95% of the density, like 95% of the bell curve around the coefficient that we found is between these 2 points, right? The problem is, right, that like it doesn't actually, like our coefficient might be like really extreme. So in reality, if we make a bell curve that's centered around like the coefficient that we got, like in our regression, that's not the same as the bell curve of like the true parameter, right? Like it's not, we don't know that the coefficient from our estimation, from our regression, is the same as the coefficient like in the real world. So yeah, I wouldn't believe confidence intervals. I don't really look at them.
Okay.
But this is the definition.
And this is for machine learning, right? Because in this case, we randomly choose like samples from a population.
Actually, no, like confidence intervals, no, we don't use confidence intervals in machine learning, thankfully. Machine learning, you won't see confidence intervals. I mean, you'll see No, yeah, you won't see confidence intervals. You'll see something called like error bars, like standard error, which is a little more reasonable. Confidence intervals come from like statistics, like old school statistics, and they're kind of
Because
going away.
I remember we have like a function to calculate confidence interval. So I thought it should be like a fixed number each time you run a model.
Yeah, no, it is a fixed number every time you run a model. The point is just that if you reperform the experiment, meaning like you recollected all the data, right? Like if it's like a survey and you ask people like, I don't know, do you like the president? And then you ask 100 people that, and then you find, or let's say you ask them, do you like the president? And then you ask them their income, right? And then you find the regression coefficient of income, the effect of income on do you like the president? That gives you like a confidence interval, right? But you don't know that you can't say you're 95% confident that that confidence interval contains the true population, like in the whole US, effect of income on do you like the president. What it is saying is like, if you kept doing that experiment, like then now you found 100 new people and you asked them and you ran the regression, and then you found another 100 new people and you asked them and then you performed the regression. If you did that like a bunch of times, on average, the confidence interval would contain the true value 95% of the time.
Got it. Thank you. So we're like choosing new samples to run a new.
Yeah,
Okay,
like starting from scratch every time. That's what it means by reperforming the experiment. Like not reperforming the regression. That might be the confusion. It's not reperforming the regression. It's reperforming the whole thing from scratch. Yeah, it's a weird thing because usually you can't. Like, I mean, maybe I'm biased, but it's just like in my dissertation, like my sample is like countries. So if I just have data on all the countries, I can't really go and like do it again with different countries because there's just like 200 countries in the world. So it doesn't really mean much for me, but yeah, usually like if you read like statistical reports by like good statisticians, they won't talk about confidence intervals. They'll talk about they'll talk about two things. They'll either talk about the error bars, which is just you take the coefficient and then you take the standard error. Like we'll see in the regression table, it reports a coefficient, but then it also reports a standard error next to it. And then they'll just say like, we think, this is our guess as to the coefficient, but this is how confident we are. The bigger the standard error is, the less confident we are. And that's helpful because you just look at like how wide that is, but that's not a confidence interval. A confidence interval is something different. Oh, and the other thing is like in Bayesian statistics, right? If you do Bayesian instead of frequentist, which is we've been doing frequentist in this class, if you do Bayesian, you can actually get a thing called like a posterior density interval, which actually like is what you want, which is 95% chance that the parameter is in here. But you can't get that in like the statistical paradigm we use in this class. Anyway, if it comes up, just remember that this is the definition and don't use it in real life. True or false, if our p-value is not low enough to meet our significance threshold, so like say it's not below 0.05, then we reject the alternative hypothesis and we accept the null hypothesis. And you have to read that carefully, but it is false because we never accept any hypotheses, right? In this case, we would just reject the alternative hypothesis and fail to reject the null hypothesis, right? Because science uses a falsificationist paradigm. Yeah, nice. Yeah, science is a falsificationist paradigm, which means we're never proving anything true. We're just proving things false, right? So we can reject things, right? Here we reject the alternative hypothesis, but we can never accept things. We just fail to reject them. And I know that's another thing that is hard to wrap your head around at first, but yeah, like if you took like philosophy of science classes and things like that, you'll start to see why. It's because like if you accept something, then it's like it's over. Like you are done. Like you know it's true, and so you don't ever check it. Whereas in science, we want to constantly be like, okay, wait, but what if that one experiment was just weird, right? Like what if, because there's like random noise, so it's like we would want to try things over and over again, right? And each time we try it, we don't know, like each time we do, like, you know, the Newton experiment where it's like he saw the apple falling out of the tree, or I guess it fell out of the tree and hit his head or something. And he was like, I wonder like what speed the apple falls to the earth at. And he like computed the gravitational constant, right? So even like gravity, people didn't just say, oh, gravity, like this is how gravity works, right? Which was good, because then in the early 20th century, they got like figured out relativity and quantum mechanics, right? And it turns out gravity only works like that, like at macro scales and at low speeds, right? So like speed's not near the speed of light. So the point is just like, yeah, we don't ever say that things are true, because then we're like done with them. Like if they're true, then they're true and it's absolute. But yeah, we also don't really like prove anything false. Like false, it's right, like rejecting the alternative hypothesis is kind of just like, in this experiment, we don't reject it overall. So I know it's weird, it's all fuzzy, but the point is just like, we can get more and more and more and more confident in a hypothesis, or we can, so that it approaches like 100% certainty, but it never hits 100% certainty. Or we can be less and less and less and less confident in the hypothesis and it approaches 0%, but it never hits it, because then it would be over. And you can always do more experiments to test like whether all the experiments before it were a fluke. Oh, true or false? Yeah, for pd.readcsv, dataset.csv, to work correctly, dataset.csv must be in the same folder as our notebook. That is true. Because yeah, the only time that you can just give it the name of a file and it will work is if that file is in the same folder as the notebook that you're working in, right? Otherwise, we have to actually tell it how to get to the CSV file from the notebooks folder. So that leads to this question: what about pd.readcsv? And then there's a .. / dataset.csv. Yeah, what that does is that tells pandas to look one level above the folder containing the notebook. The 2 dots just means go up a level, right? So yeah, if we were in home/data science project/mynotebook.ipynb, right? That means that my notebook, that's the notebook you're currently working in, is in this folder, data science projects, right? So the ... here would mean go up one level. So instead of looking in data science projects, now look in home, just look in /home. All right, regression questions. So yeah, we're gonna load a data set that has GDP per capita and level of inequality. So for each country in the world. And level of inequality is measured by this thing called the Gini coefficient, which it's good to look up and learn what it is if you don't know it. It's from economics, but it's not that hard to explain, but you just, yeah, it would be 0 if everyone in the country had the exact same amount of money, and it would be 1 if everyone had it would be 1 if a single person in the country had all the money and everyone else had 0. Yeah, so exactly, thanks Sky. It measures the level of inequality of wealth, right? Yeah, you can look up, it's like not, I could explain it, but it would be a digression. Then we'll perform a regression where GDP per capita is our independent variable and level of inequality as measured by Gini coefficient is our dependent variable, right? And so what we're saying is like, we think that we want to find out what happens like as a country gets wealthier overall, right? GDP per capita measures like the overall wealth of a country. Does it become more unequal? Like as countries get richer, do they distribute the wealth more evenly or less unevenly? Or yeah, more unevenly or more equally as they get richer, right? So first thing that you want to do when you do something like this is you want to write the equation for the unfitted model, right? Unfitted means we have not found numeric estimates yet, right? Like we haven't performed the regression yet, but we write our regression equation, and here it is, right? It says that we're saying that the Gini coefficient for some country I, that's all that I is equal to, we have the intercept, and then we have our coefficient on GDP for that country, and then we have an error for that country, right? Epsilon. It just means that, like, if we didn't have this epsilon, we would be assuming that every single country could fall on a straight line, when we know that won't be the case, right? Even if we do find our best fit line, some countries will be above it, some countries will be below it. That's what this epsilon lets us account for. So every country's Gini coefficient, we say will be some line, right? Because this is just ax plus b, but there'll be some error off of that line. And what is the null hypothesis that this regression is testing in terms of this equation, right? The answer here is going to be the same in any like ordinary least squares linear regression, right? When you do an ordinary least squares OLS regression, you are always testing that your null hypothesis is always that the coefficient on your independent variable, right? In this case, B1 is GDP, is the coefficient on GDP. Our null hypothesis is always that it's 0, right? And so in words, then that null hypothesis is that an increase of whatever unit in GDP, in this case US dollars, per capita is not associated with any change in inequality, right? Because if it turned out that this beta 1 was 0, then, right, if you plugged in 0 there, then increasing and decreasing GDP would have no effect on the Gini coefficient, because it would be Gini coefficient is beta 0 plus 0, 0 times anything is 0, right? So changing this variable, if beta 1 was 0, would have no effect on Gini. So it's not associated with any change in inequality. And therefore, the alternative hypothesis, right? The nice thing is once you have the null hypothesis, you just negate it to get the alternative hypothesis, right? So now if we write the alternative hypothesis in terms of the equation, we just get beta 1 is not 0, right? And so in words, that is that an increase of $1 in $1 US in GDP per capita is associated with a change in inequality. Cool. So this is just code you can look at whenever I just loaded this data set. I renamed some columns. I dropped the NA values, if that helps. And then since this data set has like observations for every year, this line of code looks a little tricky, but all it does is it groups it by code is just the country code. So like US is USA, Afghanistan is AFG. It's just a 3-letter code. So I just grouped it by that code, and then I took the last, meaning like the most recent observation, right? And then I imported our stats models package that we know and love. And I ran the ordinary least squares regression where Gini coefficient is my dependent variable and GDP is my independent variable. Called .fit on it. And then this, don't worry about this part. This is just so it fits on the slide. This is what you would want to call, right? Result.summary. And you call that and you get the regression results, right? And now we can finally sort of take the things we've been talking about and map them onto this table, right? So I think I've talked about this before, but even though like most of the space is taken up by this up here and this down here, it's actually this middle table that you really care about, right? Because this column gives you the coefficients. This column gives you the standard errors I was talking about. So like in this case, like on the intercept, we estimate that it's about 42 and the standard error is about 0.9, right? So like if you were giving a report on this, you were reporting the intercept, you'd say, well, it's about 42, but you'd put bands around it, right? You'd put error bars around it that went in at 0.9, above 42, so to about 43, and then went 0.9 below 42, so to about 41. So in this case, our bars would show like the intercept is, we would guess somewhere between 41 and 43. Right, and notice that that's different from the confidence interval. So, cool. So now what does the negative 0.0002 in the COEF column of GDP row mean, right? So what does this mean? This is important because like you're almost surely gonna get a question, at least somewhat related to this, and like it's a free one, right? Because you just have to make sure you get the order right. And to make sure you get the order right, just remember what our hypothesis was, right? Our null hypothesis was like GDP has no effect, or changes in GDP have no effect on inequality, right? And so this coefficient tells us the answer to that. It says, what is the effect of a change in GDP, a 1 unit change in GDP, in this case it's per capita, on the dependent variable, which is the Gini coefficient in this case. So, good. Yep, so what this tells us is that a 1 unit increase in GDP per capita, so in this case, a $1 increase in GDP per capita is associated with a decrease of 0.002 in Gini coefficient. So if that's significant, if we believe that, that means that, right, as countries get wealthier, usually their income, the wealth of the country becomes more evenly distributed, right? Because lower Gini coefficient means more equality. Cool. So that's what that means. Yeah, decrease of 0.0002 in Gini. Now, which column do we look at to obtain our p-value, right? As I didn't get to that yet, but yeah, coefficient column here, standard error column here. This is our test statistic right here. And then right next to the test statistic is our p-value, right? The probability of getting something, that's why it's like greater than absolute value of t, because it's the probability of getting a test statistic as extreme or more extreme than that t-value, right? And then there's our confidence interval. So in this case, we look in this column to get our p-value. And our p-value is 0, but we'll get to that. So yeah, column with that header. Since the p-value is so low, true or false, since the p-value is so low, we can conclude that increases in GDP cause decreases in inequality. And there's another word here that should raise a red flag in your head, right? Because this is false, right? We should never draw causal conclusions from the results of an ordinary least squares regression, right? It's we're not talking causality here. If we want to get causality, we have to do much fancier, more careful things that require like a lot more samples and stuff like that. In this case, we just have association, right? Increases in GDP tend to be associated with decreases in equality. Though really, like, all that this is saying is like, on average, countries with higher GDP have lower Gini coefficient, right? Like, because the regression is just taking, computing the average Gini coefficient values for the GDP values and then just drawing a line through them. That's all that a regression is doing. Cool. And then where do we look to obtain the F statistic for our model? That's one of the few times we look outside the middle, right? And we see up here, third row, right-hand side, we get an F statistic. It doesn't mean that much to us because we don't know like whether this is a high or low value. And so really we want to look at prob F statistic underneath it. And this is scientific notation, right? That means 1.83 times 10 to the negative 6th power, which is really, really small. It's basically 0. Right, you can look up scientific notation if you want. So the F statistic is 24.73. But what does this value mean, right? We look underneath it Well, okay, what it means is like the test statistic, yeah, we get a test statistic is for the hypothesis that all the coefficients in the model are 0, right? Meaning both the intercept and the coefficient are 0. So that's like a pretty strong, that means like our model is just so bad that like just throw it out, right? The F statistic would be like, it's kind of like a emergency light. It's like if you fail the F test, your model is like really, really bad, right? Because like you can't even reject that all the variables are 0. Like none of the things you've included in your model have any effect on the dependent variable, right? But the alternative hypothesis is that one of them is non-zero, right? So listed directly underneath the F statistic, we get the probability of that F statistic, and it's approximately 0. So we reject this null hypothesis. So we think, okay, I guess we fail to reject that one of them is non-zero. True or false? The adjusted R-squared value is lower than the regular R-squared value because GDP does not explain much of the variance in Gini coefficient. And this is where, yeah, you have to just remember what adjusted R-squared is, right? Why is it called adjusted? This is false, right? Adjusted is only lower than R-squared because the adjusted just penalizes you for each new independent variable you introduce into the model, right? In this case, we only had one, right? We only introduced one, but it still penalizes us. Yeah, George. And then I guess we'll end.
Okay. Doesn't the adjusted R-squared value also take into consideration like how many like the number of whatever that was in the model?
Samples.
Yeah, samples. Sorry, I couldn't.
Yeah.
I had a brain for it.
No. That's a good point. That's a good point. Yeah, I should have said that here. It's like, but if you're looking at the same model, right? Yeah, you're right. You're right. So that's a good point. I should have said it penalizes you for each new independent variable you introduce. And yeah, it also penalizes you for having sort of like a low sample size. Yeah, good point. But like, how do I put it? Yeah, no, it's a good point. Those are both things that adjusted R-squared tries to correct for. So yeah, if you get a low adjusted R-squared, it doesn't mean necessarily that like your independent variable doesn't explain much of the variance. It just can mean like your sample size is really low. Really, it's about like, is your sample size high enough to support the number of independent variables that you have, right? Because if you have a low sample size, but a bunch of independent variables, you're trying to learn a bunch of coefficients from like a small amount of data, and that's bad. Our adjusted R-squared will penalize you a lot for that, right? So yeah, and let's see. Yeah, this is important. I'll end with this one. How would the interpretation of our coefficient of GDP change if we added another independent variable? It's important because it does change, right? Whereas in the single variable case, we interpret the coefficient as just, oh, this is the effect of GDP on inequality. Changes in GDP of one unit are associated with this change in inequality. If we added another independent variable, we'd have to reinterpret everything, right? Even that coefficient, we would now have to say it's the effect of GDP on inequality if we hold all the other variables constant, right? Or if we center our variables, like I talked about before, where we just adjust them so that their mean is 0, right? We just subtract the mean from all of them. Then we get a nice interpretation, which is even in the multivariable case, we get that it's the effect of GDP on inequality at average values of x2, right? So if x2 was like, I don't know, size of the country, it'd be like, for a country of average size, this is the effect of GDP on inequality, which I think is a nice interpretation. Cool. And then that's a good place to end because, yeah, then I move to stats. You have the link to this, right, in the chat. So there's like 10 more questions, right? There's a bunch more. And I won't spoil it, but you can, go to these slides and test yourself. Cool. So great. That's all. Have a great weekend.